Hi guys, welcome to this video. In this video I want to start with this topic on properties of triangles. So we are going to explore triangles, and this is definitely a shift from integration and integration by parts, but I'm sure I'm going to revisit that topic in the future. But for now I think this properties of triangle is interesting. So let's get started. So let's consider a general triangle. So this is the notation that we are going to be following along, and you will find the same notation in most of the books. So any angle of a triangle I'm going to be representing by a capital letter, capital alphabet. So this is going to be capital A, this angle is going to be capital B, and this angle is going to be capital C, and the corresponding sides, or the sides which are opposite to the angles, are going to be denoted by small alphabets. So this will be A, this will be B, this will be C. So this is a general triangle, and we are going to base all of our results in terms of this general triangle. So the first result that we have is called the law of sines. So law of sines is the following: sine A, let me just increase the brush size a little bit. Sine of A upon A is equal to sine of B upon B is equal to sine of C upon C, which is equal to some constant. Let's call this I don't know, lambda. So this is the law of sines, and one thing to note about law of sines is that it relates the sines of a angle to the sides, and it you can see that the ratio of sine of a angle of a triangle divided by the side, the corresponding side, is equal to some constant, as well as all of these ratios are equal to each other. So this is a very important result that I encourage you to remember, and basically we are going to add this in our toolkit, and whenever we are solving any problem and we need to refer to a formula, we will just refer to the formulas that we have in our toolkit, and we'll apply the most suitable one. So basically just to give you an idea, you can imagine the toolkit to be a very simple virtual memory that basically has all the formulas, and whenever you want to retrieve a formula you can just refer to your toolkit, and it can be as simple as just a piece of paper or your notebook, and on your notebook in your notebook you can just write down all the formulas, and again when we need to refer to a specific formula we will refer to the toolkit. Okay, so now let's move to the projection formula, and I'm not going to be covering the law of cosines in this video, maybe in the future video, but for now law of sines and the projection formula. Projection formula is actually very simple and fun, so I'll just prove it. For the proof of law of sines you can just refer to any standard textbook, it's very simple. So I'll draw the same triangle again, but I don't need to, I'll just reuse this in order to prove the projection formula. So the basic idea of projection formula is the following: we want to express any side of a triangle in terms of the other two sides. So let's think about how we can do that. So since we have this whole line segment A, we want to express this in terms of B and C. So if you want to do that, you can do the following. So draw a perpendicular. Since right now this is not a right angle triangle, we cannot apply any of the trigonometric formulae, but if you just draw a perpendicular, so if you just draw a perpendicular, and we can always draw a perpendicular, right? Just draw a line that makes an angle of 90 degrees with this side A. So when we draw a perpendicular, you'll notice that we get two right angle triangles, the left one and the right one. So what we now need to do is we need to consider one of the trigonometric formulas, which are like sine is equal to opposite upon hypotenuse, cosine is equal to adjacent upon hypotenuse. So if you just think about this, cosine, if you just consider the left hand triangle, and what I'll do is I'll take the color blue first and I'll highlight this with blue, this base of the left right angle triangle. I'll just highlight with blue because we want to calculate its length, and the reason we want to do that is because we want to express A in terms of C and B, and I'll just call this A dash because it's a constituent part of this overall line segment A. So I'll just call this A dash. So and I'll change the color to blue so you know that I'm referring to the left right angle triangle at this moment. So cosine of B in this triangle is equal to adjacent, which is equal to A dash upon hypotenuse, which is C. So if you just cross multiply both sides, you are going to get A dash is equal to C cosine of B. So now you see that we solved in terms of A dash. So now all we need to do is we need to solve for the other line segment constituent. So let's change the color to maybe red. So I'll just highlight this line segment now and I'll just call this A double dash. So again repeating the same process. In this right angle triangle we have the angle as C sorry, and you'll notice that C, we can make use of trigonometric function cosine again. So if we do that, so this is for the right angle triangle, you'll notice that cosine of C is equal to adjacent, which is A double dash upon hypotenuse, which is just B. Just cross multiply both sides, you are going to get A double dash is equal to B cosine of C. So we got A dash and we got A double dash, and A is just nothing but the sum or the addition of both of these constituent line segments. So if we just add these two, we are going to get A is equal to B cosine of C plus C cosine of P. Now this is interesting because we just expressed one of the sides of a triangle in terms of the other two sides, and if you just notice why this is called the projection formula, because what we essentially did is that we projected this line segment B on A and we just projected the line segment C on A, and A is nothing but the sum of these two projections, which also makes sense visually. So we are going to use this result and observe a pattern, and then we are going to exploit this pattern and basically come out with the projection formula for the other two lines instead of just repeating the same process again and again. So what I'm going to do is, let me see if I can use an eraser tool. Here's the eraser. Okay, there it is. Okay, so just bear with me 1 second. I'll just erase this because we don't need this anymore. Alright, so we have this projection formula in terms of A, and I want you to notice the pattern. First of all, on left hand side we just have one side of a triangle, which is just A. On the right hand side we have the other two sides of a triangle, and the other two sides of a triangle are multiplied by this cos term, the cosine term. And if you just observe the pattern, if we have B here, it's multiplied by cosine of C. If I have C here, it's multiplied by cosine of B. So I think there's definitely a pattern. So if I want to repeat the same formula for the other sides, B and C, I can definitely do that. So B is equal to the other two sides, so I'll just like to remember like this: b is equal to a plus c, and then since I have a here, I'll multiply this by cosine of c. So cosine of c. Since I have c here, I'll multiply this by cosine of a. So c cosine of a, and c, I'll do this for this c is equal to a plus b, and since I have a here, it's going to be multiplied by cosine of b, and since I have b here, it's going to be multiplied by cosine of a. So there you have, we have these three corresponding formulas for the projected sides, I mean the sides of our triangle, and in terms of the projected components, and these are called the projection formulae. And we are going to remember all these formulas and put these formulas into our toolkit, and we are going to be referring to them when we need them. So now let's just move to the problems. Let me change the color to black, and now let's just do black over white over black for now. So the first problem is, we need to prove this: b plus c cosine of a plus c plus a cosine of b, c plus a cosine of b, plus a plus b plus a plus b cosine of c is equal to the perimeter of the triangle, which is just equal to a plus b plus c. We need to prove this. Now let's pause for 1 second and let's think about the approach that we are going to be following. So if we just refer to the toolkit that we have two formulas currently. One is the law of sines, or the sine rule, and the other one is the projection formula. I think it makes sense to go with the cosine rule, because everything, I mean the projection formula, because everything is in terms of cosines and nothing is in terms of sines. Okay, so if we decide to go with the cosine rule, I think you will observe that when you expand out these terms, we can directly apply the projection formula. So let's do that. We have three terms on left hand side, and each term gives rise to two terms, so in total we have 6 terms. So let's just expand these. So b cosine of a plus c cosine of a plus c cosine of b plus a cosine of b, this is b, plus a cosine of c plus b cosine of c, and we are done. We have 6 terms. Now you'll notice that if you just recall the projection formula from the toolkit, you will notice that, so if we just consider all the sides one by one, so let's just consider a is equal to b cosine of c, so b cosine of c plus c cosine of b, so plus c cosine of b. So instead of these two, we can just write a. So you can just imagine we replace these two terms by a, and we can do that because in fact a is equal to these two terms. Now just recall the cosine formula for b. B is equal to c cosine of a, so cancel this, plus a cosine of c, so a cosine of c, cancel this. Instead of these two, we are going to write b, and now c is equal to b cosine of a, so cancel this, plus a cosine of b. So instead of these two, we are going to write c. So now notice that left hand side is equal to b plus a plus c, and which is equal to a plus b plus c. So we just solved or proved this equation, and you'll notice that our initial goal was correct, in which we decided to go with the projection formula based on the fact that everything was in terms of cosines. So it's very important to make sure that the initial goal while you're solving the problem is correct. And I think I'll do one more problem. So let me just create a new page, and this time let's do white over black. So white over black. Alright, so the second problem involves a square cos 2b and b square cos 2a plus 2ab cos a minus b, which is equal to c square. We need to prove this actually. So let's again think about the initial goal that we need to set. Everything here looks in terms of the sides as well as the cosines of a triangle. So again, it makes sense to go with the projection formula, but even if you decide the initial goal, we need to decide a sub goal, because there are two ways to approach this problem. We can start with left hand side as well as the right hand side. So again, just by using the I guess seeing the nature of the problem, we are tempted to go with the right hand side, because right hand side looks very simple. There is only one term, which is c square. So let's see what happens when we simplify the right hand side. So just remember, c is equal to, or just recall by the projection formula, c is equal to the following: a plus b cosine of b, b times cosine of a. This is c. C square is nothing, just the square of this term, and we can simplify this. It's a square cos square b plus b square cos square a plus 2ab cos a cos b, right? So you'll notice that we cannot simplify this any further, or it doesn't make sense to simplify any further. For example, changing cos square into something else. So what we'll do is we'll just leave this here, and we'll move to the left hand side. And if we can somehow prove that left hand side is equal to this simplified RHS instead of c square, we are pretty much done with the proof. So let's see if we can do that. So the left hand side is equal to a square, and I'll just simplify to cos 2b. So cos 2b is just equal to cos square b minus sine square b, right? So cos square b minus sine square b, and then plus b square. Cos square a 2a is just equal to cos square a minus sine square a, right? And then plus 2ab cos a minus b is just equal to 2ab cos a cos b plus 2ab sin a sin b. So I think it's very simple. Plus 2ab cos a cos b plus sin a sin b. So sin a sin b. So yeah, so just to contrast, we have the right hand side above, right hand side is here, and left hand side is here. So let's see if we have anything in common. I think it must be obvious to you that we have a lot in common. In fact, you'll notice that all of the terms in the right hand side are present on left hand side. So let's cancel those terms. A square cos square b, a square cos square b, b square cos square a, b square cos square a, 2ab cos a cos b, and 2ab cos a cos b. We are still left with some terms on left hand side. So we are left with minus a square sine square b, b square minus sine square a, and this final term 2ab sin a sin b. So at this point we cannot simplify this any further. So let's refer to our toolkit again, and let's formulate a new goal. So if you just refer to the toolkit, you will see that we have law of sines present. So we can make use of law of sines here, since we have everything in terms of sines now, sines and the lengths of the triangle or sides. So if you just consider the first term, which is a square minus sine square b, if we can represent sine square b in terms of sides, we'll get, I'll make sure, so let me do this. I'll just make use of eraser. Oops. So let me just create a new page. Actually, I'll just try to write the result here, since it just involves a single line. Just ignore this for now. Okay, so sine square b is nothing but k square b square. So this is minus a square k square b square. This is what the first term is equal to based upon the sine rule, and then plus b square minus sine square a square is just equal to minus of a square k square. So you'll notice that these two terms become the same, so we can just write 2 times minus of this and just cancel this, because these two were the same. And now for the last term, we have 2ab. Sine a is just equal to k times a, sine b is just equal to k times b. So now we have 2 times, and if you just add the exponents, we are going to get 2 times a square times b square times k square, and this is exactly what we have here. So we can cancel these two, and we are left with 0 is equal to 0, which means this equation holds, which means we proved the result. So if you just consider what we did, we just formulated the initial goal. Based upon the initial goal, we solved the problem, and then we reached an intermediate stage in which we re-referred to the toolkit, in which we had the formulas, and then we started a new goal, and based upon that we solved the whole problem. So I think you'll appreciate the nature of the logical approach versus just like rote learning all the formulas, which maybe there are hundreds of formulas, which I don't think is the correct approach. We need to take a systematic approach, and that's what we did in this video, and that's what we'll do in like remaining videos on this topic. So I'll see you in the next video. Thanks for watching.